Looks like you did. Is the lighting okay today? Everything's good? Did we change anything? All good? Okay. There's what? Oh, okay, yeah, now there's a bar. I thought I clicked on it. You did again? Okay. Something happened twice. It's what? Okay, all good. Okay, we'll still wait for 2 minutes to start on time. All good. I don't see the video online, but maybe you guys can solve it while. Okay, let's get started. So today we're going to talk about simulation. You've done a lot of simulation during your assignments, of course. So it's kind of odd to talk about simulation, but this is something we should talk about because it changes. It's a really important tool for architects. Everything good online? I don't need to worry about it. You guys handle it. And you will do more and more simulation. So there will be assignments that you deal with. But this is an interesting tool that architects have that enable exploration of things that are not there yet. Meaning if you have an idea, how do you test it? It's very difficult to test every single idea by implementing it. If you actually have an idea that you can implement it, maybe that's not a very forward-looking idea. It's good to think about that way also, right? If you can already implement an existing system, that means you can do it with existing technology, right? Yes, it could be a very new idea. It could be creative, novel. It could improve things. No one has thought about it. So it could have all of these good aspects. But the aspect that's missing is it's doable in existing technology. It's not forward-looking enough. What about 10 years later? What if the technology is very different, right? If basically simulation enables you to test things that are not doable in existing systems, existing technology. And I think that's why this is really fascinating. It does also other things. With simulation, you can also model existing technology, right? And that's what we're going to talk about, that aspect of simulation also. But in architecture, simulation is used to evaluate things that you cannot build today, or it's too expensive to build, or for various reasons you don't want to build, as we will discuss. Okay, so we're going to especially focus on simulating memory systems. But what I'm going to talk about is also going to be general simulation. But I put memory over here as well. I also think about it as evaluating new ideas for new architectures in general. So there are many evaluation methods that one can follow. Basically, if your goal is to assess how an idea will affect the target metric X, where in an architecture, There are many evaluation methods that are available to you as an architect, right? One is theoretical proof. You can go and somehow theoretically prove that your idea will be good for target metric X. This is usually very tough in what we do in architecture. First of all, you need to be able to have a good model of the system, and you need to be able to prove something. This is in general very difficult, right? Because it's very difficult to have a theory of every workload, for example. You may constrain things to a very small set of workloads with some very simplifying assumptions. Even then, theoretical proofs are very difficult, especially when you talk about performance, energy, etc. Correctness, maybe. If you think about correctness, maybe there's a way to theoretically prove that your idea is correct. But that may also be not easy to do, right? Especially, we've seen, for example, a lot of robustness issues from the very beginning of this course, right? How do you theoretically prove that what you design is correct? The DRAM you design is correct? Well, good luck. You have bit flips, and those bit flips happen that are beyond the boundaries of what you can express with theory, right? At least today. Maybe in the future that'll change, but it's a very difficult problem. That's why people or architects normally resort to something else. And that something else is everything else that's going to be on the slide. It could be analytical modeling or estimation. You can analytically model a system based on, for example, requests per second, and you can try to see how what you do affects requests per second. So you need to model the workload in some way if you want to do that. You need to model the system. It's possible to do this. It's not exactly accurate, but in some cases you can actually do this. We may talk about that later on, but I'm not going to focus a lot on that. I'm going to focus a lot on simulation because this is actually the most general purpose method for evaluating things, right? Here, you're basically bound to what you can model analytically. A workload is very difficult to model analytically in general because a workload is very complicated. Existing systems are also very difficult to model. You can model parts of the system and some of the metrics. For example, memory bandwidth, right? Perhaps you can model memory bandwidth analytically and see if you improve memory bandwidth by this amount and under some assumptions, if your workload is streaming, etc., you will get this much better performance. Not so easy. So simulation is very general purpose in the sense that you simulate a system, existing system or a system that you envision, and you run a workload on that simulation, and you basically see the results. Assuming you've done things correctly, you should be able to get a reasonable result over here. And that's what we're going to talk about. Of course, it doesn't end here, right? Simulation is one level of doing things, and there are many different degrees of abstraction and accuracy of simulation, which we're going to talk about. You can do prototyping, right? You can go and say, oh, I'm going to evaluate this idea on a platform that I can build today and maybe get some results that can resemble what I would get if I actually implemented my idea in the future. Maybe possible, depends. Again, you're constrained within the boundaries of what you can do with a real system today. For example, FPGAs. FPGAs can enable you to get an idea of, okay, if you design an accelerator, maybe this workload will be this much faster. It's possible, right? Again, within the constraints. This may not be able to tell you the performance you get in a memory-centric system, right? Because that FPGA is not memory-centric fundamentally, and you're trying to do something memory-centric inside DRAM, and this may not be a good match. This prototype may not be a good match for what you're trying to do. So sometimes this is possible. Many times this is not possible, especially if you cannot build the prototype. Of course, you can always build a specific prototype for your idea. You can say, oh, I have this idea and I'm going to build a prototype. That's possible, but that's a lot of cost. And finally, you can also say, okay, I'm going to implement my idea in real life, build a chip, and see how it affects target metric X. For example, I have an idea on designing processing in memory systems, block bitwise operation processing in memory. I'm going to put all my resources to build a DRAM chip to show this. Possible, quite expensive. Is it worth it? Good question, right? Maybe not worth it, because what you will find out may not be very good. So is it worth it to go to a real implementation for every single idea that you may have? Probably not a good idea to do that, right? That's why I think having some things in the middle is very good. Analytical modeling, simulation, and prototyping. In the end, real implementation gives you the highest accuracy, probably, with a caveat. Caveat is your real implementation is as good as how you implemented it. meaning you cannot, after you do the real implementation, you cannot explore too much, right? If you designed your real implementation to be flexible so that it can do exploration, of course you can explore a little bit, but then it becomes like a real implementation doing some exploration as well, right? So this is very expensive in the end. That's why, in general, you do this only when you're really comfortable with all of your design decisions and you want to make money out of it, perhaps, right? Or you demonstrate the concept to the next level. Okay, that's why architecture is usually at the simulation level, and then you explore the space. Make sense? So we're going to talk a lot about simulation. But before I go into that, I will mention that prototyping and testing is useful still in architecture. And you've seen testing platforms. You're going to see more of those in cutting-edge research lectures that we'll have soon. We build a lot of infrastructure, test memory chips, for example. These are the soft MC and DRAM vendor infrastructures. So here, clearly, this is not simulation. This is a real platform to test chips or prototype some ideas in the memory controller or tester, and still useful, but it's limited, right? Now, the good thing is you can actually stress test chips and figure out new functions in DRAM, as we have discussed in earlier lectures, like we discussed, for example. You can violate the timing parameters. They can get a glimpse of what may happen in the future, but essentially, you're limited to what you can explore with this sort of platform. It has a different kind of usefulness, right? Okay, and then there's more work in this area, as we have discussed. You can take it kind of to the next level. Ataberk is going to talk more about that later in this lecture, but you can build a prototyping platform that kind of emulates or that is capable of actually executing workloads. Now, this is more like a prototype. The previous was more like a testing infrastructure to test different things. You could build into a memory controller prototype, etc. But now you can actually have a prototype where you could design the system such that the system can do, for example, row clone by violating the timing parameters, or generate random numbers, again, by violating the timing parameters. And you run an application, you do the hard work to actually hack the operating system and the hardware so that you can run an entire application, maybe not all applications, some of them, and you'll talk about that probably. And you get some results. And that is actually not a bad thing to do also, because this gives you an example result on a prototype, which is real. It's not simulation anymore. But now you're constrained to what you can do on the prototype, right? You're constrained to what you can build. Right? Make sense? I'm just showing you all of these so that we're going to distinguish simulation from this. You could also run a simulator on this prototype. You can accelerate the simulator, but we're going to talk about that. But this is prototyping, essentially. And this is an example of what you can get with prototyping. Ataberk will talk more about that, but essentially here, in this work, we show that you can improve initialization and copy performance by a lot. And if you recall, these numbers are huge because we're restricted to what we could do in that prototype. The processor is a wimpy RISC-V core, 50 megahertz, 50, which is really not representative of high-performance processors today. That's why you get these huge numbers. In simulation, you're not restricted to 50 megahertz. You can simulate a huge range of megahertz or gigahertz, and then you can see the effect of how fast your processor is, what kind of techniques your processor employs on the performance benefit you would get with an idea like row clone. Right? So it's good to distinguish that. That's why simulation is a whole lot more powerful. It may be potentially less accurate, but be careful about that. Less accurate within what, right? Here, you're limited to the accuracy of your prototype. In a real implementation, you're limited to the accuracy of your real implementation. Accuracy meaning goodness of your real implementation. It may be accurate. It can execute everything correctly. But it may not be good accurate in the sense that you implemented something that doesn't perform really well. Right? So even if you implement something in real life, that doesn't mean that you've done justice to the idea. So it's very important to be careful about this. And this is always true. That's why I think in a lot of cases, the big improvements in architecture come from ideas. Meaning you generate an idea, you do your best to evaluate it, you show results, and people, including potentially you, take the idea and say, forget about the results. I don't care about those. I care about the idea. I care about the implementation, maybe. Now I'm going to take it and put it on the system that I'm building. I'm going to test this idea. I'm going to figure out how I can make it work in my system. Now, this also and this also opens up a question, right? What is important, the idea or the evaluation? In the end, both have value, but in a sense, idea is a whole lot more important, because once you have the idea that no one has had, and you evaluate it and you show some benefits, what you're doing is you're inspiring someone else to evaluate that idea on their own, because they're not going to trust your results if they know what they're doing, in my opinion. Because you've done something, it could be completely reproducible, and that's good. It just may not fit their system, right? Because they have a different system and that they want to build, and they like the idea, and they are convinced of the evaluation. They have to test it again, basically. So I think it's good to distinguish the idea versus evaluation thing. Okay, so basically, that's one of the reasons why we simulate in the end, because there are a lot of ideas that we want to explore, and we want to identify the impact of those ideas on a particular system that we're trying to build, or particular thing we're going to explore into the future. And there's a lot of difficulty over here. Right? Basically, the answer you get is usually workload dependent, meaning workloads affect things a lot. And we've discussed this a lot in the course of 23 lectures. Different workloads have different characteristics. And one idea that may work for one workload may not work for another workload. Caching, for example, something as fundamental as caching. It works nicely for things that have locality. It works terrible for random access workloads, clearly. Right? So you will need to test a lot of workloads to understand the idea. Yeah, I've discussed this. Pipelining, for example, or any idea we talked about in these lectures. And workloads change, meaning you will need to evaluate. Basically, you're as an architect, you're designing a system that will be used into the future, right? Always, because it will take time to design that system. And that time, if it's 5 years, then workloads change a lot probably, and you may miss the boat. If it takes like six months to design your system, still workloads change. So you will need to design a system that works for the workloads that you're going to target. On top of this, and then there may be many workloads, right? In a general purpose design, for example, you may be designing for many workloads, thousands of workloads, maybe millions of workloads. Of course, it may be difficult to evaluate all those millions. On top of this, you make many design choices. Even if you build something as simple as an accelerator, this is not to mention that accelerators are simple, but they're definitely simpler than general purpose processors, for example, right? Even if you build something simple, there are a lot of design choices that you need to go through, right? Clearly, there's processing, there's memory, there's storage, etc. And an architect needs to decide many ideas and many parameters for a design. So now this is becoming intractable in a sense, right? And it's not easy to evaluate all possible combinations. Even if you design the fastest simulator, it's not easy to evaluate all possible combinations. That's why people actually propose machine learning techniques to explore the design space in simulation to find, let's say, profitable or useful combinations to look at. On top of the system, parameters may change because you don't have just the system design choices, but maybe different kinds of operating systems, different kind of compilers, different kind of system software that may take advantage of the underlying hardware, right? How do you actually evaluate that? Now the complexity of evaluation increases. So simulation is really designed to target some of these. For example, if you design a real system for every single idea, you're limited to what you can evaluate, right? So you cannot design a real system for, let's say, a design space that has a million different points. You design a million different systems and then compare them. That makes no sense, right? So a real implementation is, in general, not a good thing to try to do for design space exploration. But that's why we simulate. Well, that's one of the reasons why we simulate. And I call this the field of dreams, right? Essentially, an architect is a dreamer, a creator. You create something that didn't exist before, or you modify something in a way that is in a novel way, or maybe not in a novel way. You're just exploring the design space that of known ideas, and you try to decide which ideas to use. Right? And simulation is really a key tool to enable decisions. It allows the evaluation and understanding of non-existent systems, essentially. And essentially, you can explore many dreams. You can think of it that way. And we actually saw a lot of dreams in this course over the course of 23 lectures. There were a lot of ideas, right? These are actually, some of these are actually real dreams. You may come up dreaming one night and you say, oh, okay, let me try this idea. That happens a lot in research. And some of these ideas may have been dreams, and they may have become real over time. It also enables a reality check of the dreams, if you know what you're doing again, right? Basically, you may dream something, and you may think, oh, this is a great idea. And then if you evaluate it, maybe you'll find, okay, this is a very bad idea. So it's good to have that reality check, assuming you're doing things right. It can also enable deciding which dream is better, right? You may have multiple dreams, and you may want to pick one of these ideas, and you don't know how. Well, if you build a good simulator, that can enable you to figure out how. Now, these are the good things about simulation. There are also bad things about simulation. Basically, you can fool yourself with your dreams if you don't know what you're doing or if you didn't do the things right. So your simulator may tell you, this dream is good, this idea is good, but in reality, it's not good. And you don't want to figure out that reality by building the system and wasting a lot of money. And other things also, right? You could have worked on some other dream. So there's opportunity cost always. Because when you focus on one idea, there's also opportunity cost of lost time you could have spent on some other idea. Okay, so we need to be careful, essentially. So clearly, there are many levels of simulation also, right? A simulation can be extremely detailed, extremely low level. It could really match for example, you could do circuit level simulation. You could model a processor with all the circuit effects that are going on, voltages, currents, etc. This will take a lot of time. It's very time consuming. That's not the lowest level. There's also a lower level where you can model the electrons and devices, etc. Right? That'll take a lot of time. So we're not talking about that level of simulation over here, but clearly there is work that goes on at that level of simulation when people actually look at different circuits. Actually, we saw some of that when we talked about, for example, doing tiered latency DRAM. There's some circuit level simulation that you need to do to decide what is the impact of these isolation transistors on the latency of the bit line, the power of the bit line. Right? That's a level of simulation that you can do in a targeted way. But if you actually try to simulate the entire system at the circuit level, that's also very expensive. It's almost like building a system. Maybe even harder, because you may need to know the parameters of the circuit, right? That may be difficult. And then there's a slightly higher level simulation, well, not slightly, higher level simulation, which is more closer to architecture, more logic level simulation. We call this RTL simulation, register transfer level. And this is also slow. Basically, you simulate things at a gate level, a register level. And what you have is still very close to a real implementation, but the simulation abstraction is at the gate level. You don't deal with voltages, currents, etc. You deal with really logic at that level. And clearly, people do that in RTL, Verilog, VHDL simulation, and people who have taken the DDCA course have done it multiple times, many times. And you could imagine modeling everything at that level also, gate level, and saying, okay, I have a memory-centric computer. I want to understand the impact of that on many workloads. I'm going to simulate everything at RTL level. Possible, but very expensive also. Not as expensive as circuit level, but still almost intractable. Actually, I would argue that this is intractable for design space exploration because it's too time consuming to design and evaluate. Especially if you want to run a workload for more than one instruction or 1,000 instructions. Now think about million instructions. Many workloads have trillions and trillions and trillions of instructions. Right? How are you going to do that? We're going to talk about that also. That's not as an easy thing, even at the higher levels of simulation. Okay, so basically, that abstraction is too low level. I already said this. And then we talked about one workload. You want to run thousands of workloads to see. And you want to run thousands of different parameters, right? So basically, design space is too large. Okay, especially if you want to predict the performance of a good chunk of a workload on a particular design. I kind of said that. Especially if you want to consider many design choices. Even if you look at something like a cache, for example, there are many design choices. How large the cache should be, what is the associativity, what is the particular policy to do insertion, eviction, replacement, essentially all of those choices. Yeah, so there are many choices over here. And even if you just constrain yourself to a cache, this level of simulation is very slow. I kind of said that also. Block size. I forgot the block size. That's an important one. Memory control and scheduling algorithms. You can think of all of these different choices that you have in a processor and modeling this at the RTL level and trying to decide whether you want to use in-order execution or just out-of-order execution, reservation station, different types of reservation stations, etc., is not easy. First of all, you need to build the simulator. So RTL is a simulator, actually. If you think about RTL, register transfer level implementation, it's a description of the hardware. That description doesn't match the physical hardware. There's clearly a step multiple steps that happen. After you design the RTL, you need to validate it through some sort of simulation. And then you implement it. Meaning you're still at an abstraction level that's farther from the hardware. Right? The real hardware is here. And then there's RTL. There's mapping that happens after RTL. And this simulator, this is RTL level simulation, is not completely accurate also. Right? Because what you implement later is going to be slightly different. There will be design choices that are made in the mapping, etc., that will change real hardware compared to the RTL itself. So it's good to think about that. And actually, people who build processors try to look at and understand what is the disparity between RTL and real hardware, and they try to match it as much as possible. We're going to talk about that also. Yes. Exactly. Yeah, exactly. Gate level to circuit level, and also or custom design. And then once you go into hardware, you may need to change the critical paths to make sure that everything operates correctly. So there could be a lot of let's say changes that happen while you map from the gate level to the existing hardware. Some of them may be induced by the automatic mapping tool. Some of them may be induced by people who actually do custom logic or custom hardware design, custom layout, let's say, right? Because there's some layout that needs to happen also, right? Okay. Okay.
How do we know that the real world
What is bad? Uh-huh.
tell you that something is good? How do we know beforehand?
Well, we don't know necessarily. That's where we're going to talk about that, but that's where experience also comes in. This is also not a perfect science, right? Basically, I think that question triggered me to get to that quickly. In the end, what we're doing is not science. You cannot model all of these completely. It's partially science, no question about that. But a lot of it is also art, right? When you design art, that's why it's called architecture, actually. Architecture is not science in the end, right? A lot of what you're doing is also art. You need to have an intuition as to what will happen. And if you have experience, that of course helps also, right? But of course, you need to be careful, right? Experience is sometimes also dangerous because you may, like we have also seen in this course, experience may always tell you, oh, don't do anything other than processor-centric, right? So you need to be careful with all of these things. But clearly, we cannot evaluate everything, and we cannot know for sure completely also because we don't have the complete ground truth in the end, right? And we should acknowledge that. There's no way this is going to be completely ground truth. If you're not comfortable with it, don't be an architect. It's clear. Go do math, for example. Go do some physical science where you actually can do the experiment, figure it out. Of course, that may not be possible also to do the experiment sometimes. But architecture is not really complete science in the end. It's engineering. You cannot model everything, essentially. Hopefully that makes sense. Okay. So basically the answer is you don't know. But that doesn't mean that you cannot do a good thing, right? Okay. And this applies to a lot of things humans do, clearly, right? Humans make a lot of choices, and they don't know whether they made a good choice in the end, right? This is another example over here, but except I think this is a little bit better. It's still in a constrained environment where you're dealing with hardware. Once you start dealing with people and resources, it becomes much worse, right? Then you cannot actually, there's no ground truth that you can test things with over there. Here, there's some ground truth, except you may not be able to get to the ground truth or every possible ground truth to compare different things with. Okay, so basically, in high-level simulation, one major goal is to explore the design choices quickly to see their impact on the workloads that we are designing the platform for. Right? But there are different goals also. Right? One goal is what I just said: explore design space quickly and see what you want to potentially implement in the next generation platform. There are many design choices over here. What you want to propose as the next big idea to advance the state of the art. This is more of a research purpose. And researchers always try to do this, clearly. And if you actually want to do this, then your goal is to mainly see the relative effects of design decisions. Maybe you don't care about being accurate within 1% of performance, let's say. Right? Your goal is to really see relative effects. For example, I move to processing in memory using some sort of processing in memory mechanism. I get 10.5x performance improvement. Do I really care about the accuracy of that exactly? In the end, you're back to that question, right? You don't know for sure, but it gives you an idea of the relative effects. And again, you need to be comfortable with it. You need to do your best in modeling so that that number is as accurate as possible to your experience and to your best understanding, or the best understanding in the field. That's really important. You don't basically model something randomly and say, okay, declare victory. That's not what should happen. You should do the best methods. You should use the best methods that people use collectively and then see the relative effects of design decisions. This is one goal, but there's another goal, which is completely different. You may want to simulate so that you design a simulator that matches the behavior of an existing system. And this is helpful so that you can do the debugging and verifying that existing system at cycle level accuracy. Figure out, so if your simulator matches your existing system nicely, you can actually make small changes, small tweaks to the system, for example, that can make a difference in performance or energy. And this is what companies do all the time. Once you actually have a real implementation, you can design a simulator that matches the behavior very nicely. And then you can iterate, meaning you can design the next generation by changing some things in the simulator, exploring what those changes, how those changes affect the metrics that you care about. And you can do it with reasonably good accuracy, assuming your model is actually good enough. But still, there's no ground truth. The ground truth hopefully happens after you design the real implementation. And hopefully propose a much better real implementation in the next generation. Right? And this happens a lot, as I said, in companies. They actually have teams to do this. The goal here is very high accuracy so that you actually have a simulator for your real system. Make sense? So if you go to a company, you will actually, one of the things that some people do in that company is to design that simulator or tweak that simulator so that it matches the RTL. And they spend a lot of time, like their days and days and days, all their days, maybe some of them, to figure out what is the discrepancy between that simulator and the real hardware. Okay, so there could be other goals in between, of course, right? You may not want to explore the design space a lot. You may want to refine the explore design space without going into a full detailed cycle accurate design. This is basically cycle accurate or seconds accurate, whatever it is that you want to match energy accurate. You could also say that. You want to match the energy, for example, of an existing system using modeling. But you may not want to explore the design space. You may not want to match the behavior, but we may want to focus on some components and refine the explore design space. Or you can try to gain confidence in your design decisions made by higher level design space exploration. So then you go into the next level of simulation. The first one can be relatively high level, and then there could be progressive refinement. We're going to talk about that progressive refinement. Okay, so let's talk about trade-offs. In general, there are three major metrics to evaluate a simulator. There's speed, how fast your simulator is, how quickly it generates results. There's flexibility, which is important, clearly, to model different things. And there's accuracy, which is how accurate your simulator is compared to your target system. Now, with accuracy, that question actually was a good question online. With accuracy, you may not completely know how accurate you are. If you know if you have an existing system, you can. But once you try to modify things, you may not exactly know. So keep that in mind again. Ground truth is not available to you all the time. Okay, speed is how fast the simulator runs. It's usually measured in terms of how many instructions per second it can simulate. how many cycles per second it can simulate. What is the slowdown compared to real hardware, if you can measure that? Flexibility is how quickly you can modify the simulator to evaluate different algorithms and design choices. And accuracy is how accurate the performance or energy or whatever metric numbers the simulator generates are compared to a real design. And this is also called simulation error. So this could be compared to a real baseline design, which may not match what you're really trying to do. So maybe you don't really care about the simulation error as much, right? If you think about it. It may model an existing current system very well, but it may not model where you're trying to get to very well. Keep that in mind. That may be good or bad, by the way. Okay. So the relative importance of these metrics clearly depend on where you are in the design process and what your goal is, right? We saw different types of goals in simulation. Sometimes your accuracy is extremely important. If you're doing design space exploration, speed is extremely important. Usually, you cannot get the best in all of these three metrics. This is one of those examples where you can get maybe 2 out of 3, but maybe not 3 out of 3 easily. It's very hard. Okay, so it's a trade-off in the end. You need to trade off speed, flexibility, and accuracy. So speed and flexibility clearly affect how quickly you can make design trade-offs and decisions, how quickly you can evaluate them. Because it's a loop, right? You have an idea or you have a design decision to evaluate. You need to implement it. That implementation should be quick. That is flexibility of the simulator. And that simulation should run fast so that you can actually get the result and say, okay, this is a good design choice. I'm going to explore a little bit more. Whether it's a human that's exploring design space or a machine learning algorithm that's exploring design space, it's still the same. You need to run a lot of simulations to explore design space. Accuracy affects how good your design trade-offs and decisions might end up being. And I put might specifically over here because this really depends on the target, as we've discussed. And also how fast you can build your simulator, meaning simulator design time. That's another metric, actually, to think about. It's kind of a offline metric because you need to spend some time to design your simulator to begin with. After that, flexibility matters. That's the metric that you care about after that. But still, simulator design time is also important. In fact, this may make or break products. In fact, there are companies that were almost not releasing some products because the simulators were not good enough to build the products. And some people who were really good at designing simulators came in and designed a really good simulator and saved the products. I'm talking about Intel. When they were designing Pentium 4 processors, for example, they actually had a lot of trouble getting the simulation infrastructure initially. And there were people who actually were able to write simulators really well. These are really good architects, I would say. And they were able to actually explore design space and build these products in the end, which were actually top of the line products at the time. Intel, some other issues these days, but we're not going to get into that. I wish they didn't, but it's not my design choice. They could have simulated some of the other design decisions that they made, perhaps, right? Not in architecture, but something else, management. Okay, flexibility, the third metric, also affects how much human effort you need to spend modifying the simulator, right? And this is also important, right? If you have a simulator that's not flexible to modify, that's extremely complicated, then you may actually spend a lot of human effort debugging and making mistakes because your simulator is also a piece of software. It could be a hardware accelerator, as we will discuss, but it's a piece of software in the end. And that piece of software may have bugs. These are bugs that are different from accuracy of modeling, right? These are bugs where you actually have a bug in the simulator and you have to fix it, right? And a more complicated simulator usually has more bugs that may or may not have been discovered. And that's also something to take into account. So more complicated simulators doesn't mean that they're more accurate in the end. They may actually be less accurate sometimes because they try to model too much. And as a result, they become unwieldy. It's very difficult to modify them. And also it's very difficult to validate them as well. And as a result, a much simpler simulator that models things from a more first principles level can be actually more accurate. Good to think about that. Okay, so in the end, you can trade off between these three metrics to achieve design exploration and decision goals. And it all depends on your goals, as we've discussed. But it's good to consider that you cannot get all three metrics. to be maximized. Okay, so high-level simulation. The key idea I've already given you, basically, you raise the abstraction level of modeling to give up some accuracy to enable speed and flexibility. Well, maybe I didn't exactly define it this way. This enables also a quick simulator design. Right? As you keep raising the abstraction level from real implementation to higher levels, you have more flexibility to be less accurate. Right? You don't need to be completely accurate because your goal is not to be completely accurate. Your goal is to enable fast exploration and flexibility, and also a quick simulator design. Okay, the advantage is, clearly this has advantages, like every idea that we discussed in this lecture, it has advantages and disadvantages. The advantage is you can still make the right trade-offs and can do it quickly. And depending on what your goal is, this may be what you really want. The key is, all you need is modeling the key high-level factors, and you can omit corner case conditions that may not happen. Again, you need to be careful over here, but this is where experience helps. An experienced architect can have an idea of what to model and what not to model. Again, you need to be careful. And all you need is to get the relative trends accurately, not exact performance numbers, and we've discussed this. The disadvantage, of course, you open up the possibility of potentially wrong decisions. If you forget to model something important, and that turns out to be the bottleneck in the future workloads that are going to be running on your system, then you have a problem, right? Oops, you didn't model it. And that happens also, right? For example, you don't care about the virtual memory system. You don't model the virtual memory system. And workloads that are important put pressure on your virtual memory system. And you get a lot of page faults or TLB misses that you service, but you didn't model them. And you optimize your system without those effects. And as a result, what you produced will not run nicely on a system that has virtual memory. Right? Konstantinos will talk about virtual memory, I think, next week or the other week. So you will understand some of that maybe. Okay, basically the key is, how do you ensure you get the relative trends accurate? Yes. A question? Oh, okay, go ahead. Mm-hmm. Both. Yes, exactly. First of all, yeah, you need to do due diligence to what you do. If you can design your simulator, it's not easy, or you can use a simulator that's well respected, well used, well designed, and you can build on it. But this doesn't mean that you should not understand the simulator. You could do the due diligence and go and understand the simulator, how it works. And working with someone, of course, who's experienced helps a lot, right? It's good to have someone who's experienced to discuss. Good question. But you always need to do due diligence yourself, even if you're working with someone, because that's really important. Okay, so simulation can also be, yes. Yeah, I mean, you can, if you study the code long enough, you'll probably be able to discover the design decisions. But yes, it takes time, right? Mm-hmm. Mm-hmm. Yeah. Mm-hmm. Yeah, that's. I mean, it's not easy in general, but experience also helps here, certainly. But again, anyone can read software if it's released. So you're talking about the case where the software is released and you know you can go and read the simulator, and you can decide on your own, right? Okay. Oh, I see what you mean. So maybe they didn't release the software, let's say. Yeah, if they didn't release the software, then you have no way of, let's say, completely verifying that claim. Then you cannot evaluate exact accuracy. But you can still do like validation based on what you know or what collective research knows, and also internal consistency checks, right, inside the work. If one result contradicts another, and there's no explanation for that contradiction, and you cannot come up with an explanation, then that's probably something that doesn't look good, let's say, right? That doesn't mean it's incorrect, but that doesn't look good. At least it's unexplained, that there's some contradiction. Yeah, but you cannot completely verify unless you have the source code. And even sometimes when you have the source code, you cannot completely verify because source code may not match what's reported in the paper, right? There's another abstraction level over there. Yeah, that's one of the reasons I think ideas are a whole lot more important than evaluation in the end. You can look at the ideas and you can, again, this also requires art, right? Art and experience helps here. But again, experience also helps to guess whether some results may or may not be correct. Yes? Yeah.
If the simulator is not very, requires a lot of effort to do something, could be just smarter than building.
Possibly, yes, exactly. That's not an unreasonable thing to do. But that's a design choice also, right? Building a new simulator could be good because you could actually focus on what really matters for what you're trying to do. But there's always a danger of you may not be doing something right, especially if you're not so experienced to begin with, right? But building a new simulator is not a bad thing to do. Yeah, I built simulators and I like building simulators. But I'm also modified many simulators as well, right? For my thesis, for example, PhD thesis, I implemented the idea on 5 different simulators, which was interesting. And they're all different and different levels of modeling, etc. Yeah. Okay. So simulation is also, it can be viewed as a progressive refinement, right? At the bottom, you have real design. At the highest level, you have very high level abstract models. And it could be very high level language models, right? And there are medium level models, there are low level models, RTL with everything model, for example. There could be lower level models, as we have discussed. And essentially, there's inaccuracy at all of these levels. And clearly, as you refine, go down above the list, abstraction level reduces. Here, you're very abstract. You can look at very big concepts. Here, you probably cannot look at very big concepts as easily, right? Because you need to modify a whole lot in the simulation. Accuracy hopefully increases, but not necessarily. Again, it's good to keep that in mind. Sometimes a high-level model may be more accurate than a medium-level model. Flexibility clearly reduces because it's a lot harder to modify a real design, for example. Especially it's very hard-coded. It's easier to modify a high-level model. Speed likely reduces because high-level models are fast to execute. Real design is very interesting over here because its speed is hopefully much better than any kind of simulator up there. It's good to think about that, right? Especially if you're implementing a fast technology, right? Okay. And the good thing is, if you actually have this progressive refinement, you can loop back and fix higher level models. So this is what happens in companies that have a lot of experience in building products. They have real designs at some point. Initially, they start doing some simulation or maybe some analytical model. At some point, they get to a real design. Once you get to a real design, you can build your low-level models. And then you can refine what you've done, high-level models, medium-level models, low-level models. You can basically keep refining your choices. You still keep your high-level model as high-level, meaning you don't model everything, but you model the key things, or maybe you find the parameters to model things, latencies, for example, nicely so that you match what you're really trying to build, right? But you don't want to really make it a medium-level model. You still want a high-level model so that you can explore the design space. These all have their place in designing processors, right? Or whatever, memory systems. Make sense? But of course, there's a downside to that also. Yes, you may have all of this infrastructure as a company that's built, but it may not be doing something completely different. Right? Once you try to do something completely different, like processing in memory, maybe not all of that infrastructure is useful. Right? So keep that in mind. Okay, so making the best of architecture. I think a good architect in the end is comfortable at all levels of refinement. And I mean all. It's not easy, but it's good to try to do that, including the extremes, meaning very high levels, analytical modeling, and also real design. And you need to know what to use, when to use what type of simulation, and more generally, what type of evaluation method, whether you want to do the prototyping, for example, etc. And a variety of simulation evaluation methods are available. So keep that in mind. I think architecture, clearly we've covered a lot of theory of architecture. I call it theory of architecture, right? You have ideas and you can evaluate ideas. Those are all good. But then there's also the practice, or you can think of that white collar versus blue collar. some very architects that I worked with actually were thinking this way. The white collar is developing ideas, building high-level models, and then blue collar is really getting it done, right? If you're both white collar and blue collar, then you're a really good architect, I would say. Okay, so let's talk about some general issues in architectural simulation. Goal of simulation we've already discussed. Goal of simulation dictates many design choices on what simulator to build and use. We talked about the metrics, and we talked about many possible goals. I'm not going to go through this in detail, but one thing that I will say is sometimes you want to look at the entire system performance or metrics. Sometimes you want to model some components, and these are all important to look at. It's good to be able to constrain yourself. I would just want to look at this cache in isolation, right? Or SSD in isolation, or memory in isolation. You want to understand the bottlenecks. All of these can be done with simulation. Just like prefetching, you have 4 questions in simulation: what, how, where, when. What do you simulate? Do you simulate the component or full system? Do you simulate the entire programs or traces? And we're going to talk about that. Traces are actually, for example, addresses or some execution trace that you've captured, and you want to replay it in a simulator to see how it works. Or you have a binary or image of the system, and you basically simulate from that image, right? You have the entire state available, as opposed to in a trace, you don't normally have the entire state available, right? You just have instructions coming or addresses coming. Maybe you don't even have the data in a trace sometimes, right? So how do you simulate it? There are many choices over here. We're going to look at some of these over here. We don't have time to look at everything. Where do you simulate things? For example, do you do it in software? Do you accelerate in hardware? Especially with simulators getting more and more complicated, people have been proposing more hardware-accelerated methods of simulation using FPGAs, for example. You could use GPUs to accelerate your simulator also. And when do you do things in simulation? Like in simulation, the good thing in simulation is you can evaluate things that are not buildable also. Right? For example, you have a cache. You can say, I have a perfect cache. It always hits. You cannot do that in a real system, right? It's not possible. In simulation, you can do that. You basically say, I get this address, and I'm assuming that its latency to execute this load is whatever the latency of a cache hit is. So that's one of the beauties of simulation also. You can actually look at ideal systems. If I have a perfect cache, this is my performance improvement. If I have 0-cycle DRAM, this is what performance improvement that I think I'll get. If I have, perfect branch predictor, this is the performance improvement I will get. This is the energy improvement. And then you can combine all of those ideal things, and you can now figure out which ones to focus on more potentially, right? You can figure out what are the bottlenecks, what are the headrooms in improving each of those components, for example. So that's what but for this, you need somehow Oracle information, meaning you need to execute the branch, for example, to determine the direction. And based on that, you don't mispredict it in the simulator, for example, right? Or you execute like a real machine, meaning do exactly what a real machine does, and you don't use your Oracle information early. We'll briefly talk about that. So inputs and outputs, this is very general again. I'm just going to give you general things, and then we're going to look at 2 instances. One instance, MQSim. Rakesh will talk about it. Where's Rakesh? Okay, he's sitting in the back. And then we'll also talk about PiDRAM, because I think it's really important to look at prototyping infrastructures as well. But I will cover the basics. So input can be program binary, or it can be multiple program binaries. It could be system state checkpoint. We've already discussed this. It could be traces. I don't have that over here, but outputs can be essentially functional, meaning program results, statistics about functional execution. This is a functional simulator. This could be useful for debugging things at the ISA level, right? So you add new instructions, and you want to actually look at the functionality of your program, right? And if you don't get the same result that you expect to get, maybe you didn't do something right in your ISA, instructions and architecture. So there's functional simulation that happens, but most of what we're discussing so far has been timing or performance or energy, some other metric related. So you want the execution time, system throughput of programs, and statistics about timing and performance and energy events, for example. Okay, so I don't know how much time I want to spend. Let's see. I want to give enough time to MQSim and other presentations also. But so functional versus timing simulation is important. And in general, you need to do both. If you want to do timing, you need to execute the program in some way, or you need to have traces, right? So I'm going to show you some examples over here. I've already given you an idea why functional could be useful, right? So full system versus component. When do you do full system? When do you do component simulation? Again, it depends on your goal. And then what should be modeled? Once you talk about full system, what do you model? Do you model the operating system completely? Do you execute that? Do you model the virtual memory completely? Do you model the memory allocator completely? Basically, you can actually simulate everything, right? You can even simulate the program, right, at some point, right? Meaning have a simulator for the program as opposed to a real program. It's good to think about it. Where does simulation stop, basically? And where do you actually have a real, like, software that's executing on the simulator? So it's good to think about that. Do you execute the complete workload? So assume that you've defined a workload, like a benchmark. Actually, we should talk about benchmarking more in later years, maybe, or next lectures. But you said, okay, this is my workload. This is what I care about. This LLM inference workload that everybody cares about. I take. How do I form it, basically? Essentially, what are the inputs that I feed to it? Am I able to simulate the entire thing? If this thing, let's say training, like much worse. I want to actually understand whether the system I designed is good for this LLM training workload with some input sets, assuming you've solved all of that input set issues. This is the thing I'm going to simulate. Let me simulate this entire workload. It'll take 1,000 days in real life, maybe, to train things. In simulation, multiply that 1,000 by 1,000, maybe. That sounds good. I'll wait for 1,000 times 1,000 days. And then you'll never design that system. That's a large number, right? 1,000 times slowdown is not unreasonable in a simulator, actually. You'd like to ideally reduce it, but 10x. If you do 1x, maybe simulator is as good as but that's not easy to achieve. Of course, depends on what you model, right? Okay. So normally what people do is they try to sample workloads. They try to find a representative part of a workload, which is a problem in itself. How do you actually represent a portion of the work? How do you find a portion of the workload to represent the entire workload, or at least like a large fraction of it? And there's a lot of work in this area on figuring that out. Or you could actually sample different points in the workload and hope that you've sampled enough, and that gives you good accuracy. But simulating an entire workload today is, unless that workload is a Mickey Mouse workload, which means it's a simple workload, is almost out of the question, essentially. Right? So it's good to think about that. Now, you can actually do things that alleviate some of these concerns, meaning you can do some micro benchmarking, for example. You design a micro benchmark, and you say, this is what I expect this micro benchmark to do because I crafted it, and it's going to be streaming, and that's all it's going to do. And you can do that, and this is good for validating your simulator. So using micro benchmarks that you know how they will behave on a given architecture is very useful for validating your simulator. This doesn't mean that that's enough, right? You really need to simulate workloads. And then there's also another issue with simulation, like simulated structures. Like you have a lot of structures, caches, branch predictor tables. How do you handle them? Do you warm them up, or do you start them cold? And this clearly affects your accuracy, right? Because in real life, clearly there are cases where you start them cold, but maybe in most usage cases, your system is running and there's some warm up that has happened, right? What do you simulate? So now we've gone into detail, right? And even this detail hopefully should convince you that there is no way you can make all of the design choices completely accurately. You can if you're living a million lives, maybe. It's going to be difficult. If you figure that out, let me know. Okay, so people have been writing simulators. This is a very old simulator, a processor simulator, single core simulator. It used to call it was Simple Scalar. I don't think it's being used by people anymore. But you can see that it has different kind of modes. There's a fast mode, there's a profiling mode, etc. There's a cache mode where it simulates the cache, and there's an out of order execution mode, which is also interesting. So this was used a lot, also abused a lot in architecture, because people use the simulator without really understanding how it works, even though it was a simple simulator. And essentially generated some numbers, which may not have been useful. So going back to maybe your question, there are a lot of papers out there that use, I don't think it's simple scalar's fault by itself. I think I fault the people who actually use the simulator to generate those numbers without understanding what they're doing. And that's the problem. So for example, one of the reasons I say this is the memory modeling in simple scalar is like this. Cycles, which is the number of cycles that you've taken to execute the program, plus equals memory latency. Basically, whenever you get a memory access, you increment the cycles by that much. That's your model. There may be a little bit more in later versions, but that's the initial version. So it's really useful when you actually, your program, this doesn't mean that it's not completely useless, at least in initial versions. Later versions clearly improve things a lot. But if you model like this, then you're not modeling a lot of the effects that we've seen in memory, right? Parallelism, locality, row buffers, etc. There's a lot that goes on in memory. You're modeling maybe infinite bandwidth if you do that, maybe not, depending on how you're modeling. It's not as simple as I just said, but it's kind of similar. This is when the request returns, actually. Yeah, but there is also not initially bandwidth. There was no bandwidth modeling also. So if you do this, if you don't know this, if you take the simulator, and if you make an optimization that is clearly affected a lot by how you model memory, then what you're going to get is probably not going to be accurate, right? You can easily tell that. Right? This is where knowing your simulator really helps, right? What it models, what it doesn't model, how it models something. But if your workload is completely cache bound, and if you're studying effects that are not going out to the memory system, which is very difficult to do today, clearly, then the simulator can be very good. So it's good to know when your simulator can be useful, and when your simulator can be completely useless. Does that make sense? Okay. Let's see how much time I want to spend over here. So functional versus timing, there are many different ways of designing simulators. I'll go through this relatively quickly. But sometimes you design a simulator. For example, what is function? Function is really execution of an instruction. You execute the instruction, you know all the results, and then you just model the timing. That's called a functional first simulation, essentially. Essentially, you have a front end of the simulator where you, which takes an image of a program, and it executes every single instruction. Now, the benefit of functional first simulation is, in general, it enables you to model things in an oracular way. For example, you can basically take an instruction, you execute it, you know all of the inputs and all of the outputs. That's good. You kind of execute in the front end. You know the correct result. If you want to feed it to the timing simulator, now if you want to model the latency of things, you can model. For example, you know that this branch will be mispredicted because you can check the direction of the branch after you execute it. And you can actually also access your branch predictor, and your branch predictor tells the direction is different. If it's different, then you can actually put the timing simulator on the wrong path, and it can execute on the wrong path, assuming you're capable of modeling the wrong path in some way, right? So that's the benefit of functional first. One of the things that is not easy in functional first is predicting values, for example. If you want to predict a value of an instruction, especially based on when that instruction executes over here, it may be very difficult to do that prediction because you've already executed the instruction over here. So essentially what you really want to do is you want to take the program on a path with a particular value. And that value, the generation of that value is dependent on timing. Meaning when you actually fetch the instruction, the value prediction has not happened yet because you're going to simulate the timing of the value prediction. Value prediction happens maybe 500 cycles later, right? But you've already executed the instruction, and you already executed subsequent instructions that depend on it at the front end of the simulator. But your timing simulator, 500 cycles later, it says that, oh, you should have predicted the value differently. Now, how do you deal with that? This is actually a headache in a lot of simulator designs, because one way of dealing with it is actually when you do the function, you checkpoint every single instruction. You can roll back to a previous checkpoint, and you re-execute with a different value, right? Now, these are very expensive things to build. So people also have done timing first simulation. That's the benefit of timing first simulation. If you know when an event will happen in a processor, then you execute the instruction with that value that you have generated in the value predictor, for example, right? So there are benefits to timing first and functional first, and there's no, unfortunately, easy way of getting the best of both worlds. And you can read some papers like this one over here. Okay, so this is another example over here where there's a functional model. This is actually a simulator that implements a timing model, I think, in an FPGA. But if you have a functional model executes every single instruction and sends the instruction traces into a timing model that accurately models the timing as much as possible. And at some point, for example, when the branch misprediction is resolved, the timing model also needs to interact with the functional model saying that, okay, I resolved the branch misprediction. Now you can go back and start feeding me the correct path of instructions, right? So you need to model these things. Some of these issues don't necessarily exist in trace-based simulation, but some of them exist. It actually, yeah, it's good to know. Okay, let's see. So validation of accuracy is important. I think this is good to think about. Like functional accuracy is important. If you don't model the functional thing correctly, then you're executing something that doesn't make sense probably. If your timing accuracy is important, your results may not be. If your timing accuracy is not correct, then your result may not be good for performance, right? There's also online versus offline validation. That's also interesting, right? You design the functional simulator, you design the timing simulator. Do you validate things offline? Of course, you should validate things offline to make sure it's correct, but maybe there's some things that you don't model. And maybe there are some bugs in your simulator. So some simulators are designed such that they also have a checker at the end. So they have a functional model at the front that takes instructions. And when you're retiring instructions, you have a checker. And that checker checks whether the value at the back end matches the value that in the front end. And if you have a mismatch, then you probably modeled something wrong. It's always good to have these validation checks or assertions in your simulator. Okay, you can accelerate your simulation clearly with hardware support, with software methods, with better software engineering. You can have trace-driven versus execution-driven simulation. I think we've kind of talked about that, but I will not go into more. But for example, if you have execution-driven simulation, you can model the wrong path more accurately, potentially. Because if you have trace-driven simulation, you collected the trace in some way, and the trace is really a trace of what is executed by the program. Unless you actually somehow collected the trace with wrong path information in it, which may not be easy to incorporate. If you're execution-driven, you're really executing the program, and you can, when you get a mispredicted branch, for example, you can actually steer the functional part of your simulator to the wrong path, and you execute it on the wrong path. Force the program to actually execute on the wrong path. And you can model all of that. Okay, I will skip this one over here because it's very detailed. How do you do state maintenance and recovery? It becomes important. Again, mispredicted execution, wrong path, wrong values. There's a lot of prediction that goes on in existing processors. And you may need to roll back the state. So you may need to do a lot of checkpointing in your simulator. And then there's also many simulator design choices that we're not going to get into, but one of them is event-driven versus cycle-by-cycle polling. For example, do you design, let's say you design a memory system simulator. Do you basically simulate every cycle? Every cycle you check whether something is happening, or do you actually have an event queue that basically enables you to take an action when an event happens, right? Usually event-driven is actually faster because you don't do unnecessary checking, but it requires maintenance of event queues, etc. Maybe actually harder to design event-driven simulators sometimes because cycle-by-cycle polling is kind of natural, right? Every cycle, something is happening, and you just simulate it. Okay. Any questions? We've covered a lot of topics. I mean, this is theory. Without actually modifying and building a simulator, this stays as theory. Meaning you will learn when you actually work with simulators. And many different simulators, because there are many different simulators with many different levels of abstraction, etc. Okay, so I'll give you an example simulator that you have already worked with, actually, which is Remulator. Which lab did you work with? The current one, okay, you're already working with maybe. But I will go through this relatively quickly because we may actually have a Ramulator lecture in one of the cutting edge research lectures. But this is a simulator that we have designed that's actually widely used in academia and also industry. A lot of industry folks use the simulator to model the memory systems that they're building, major companies. They actually have contributed with a lot of feedback to us. So it's also, once you open source things, you actually have a loop where you get a lot of feedback and you can actually improve the simulation infrastructure as well. But one of the main reasons why we built this infrastructure was to essentially study memory systems more flexibly. Essentially, there was a lot of work that you have seen in this course where work going on in DRAM and memory controller. And there were many new and upcoming standards, and these will keep coming, I think, and many new control designs to be examined. And we want the fast and easy to extend simulator, which was not available until we actually released Ramulator. And you can see some of the examples over here. This is from 2015. You can see that there are a lot of DRAM standards that people were examining. And some of them clearly have become very big, like HBM, LPDDR, for example. And if you are able to design a simulator that can model different types of memories, different types of memory controllers accurately or reasonably, then you can actually check which standard is better, which standard you want to use. And you've already seen actually research that builds on Ramulator, so I will go through this relatively quickly. So Ramulator provides out-of-the-box support for many standards, plus academic proposals. At the time, the paper was written, it was faster than the fastest open source simulator. I don't know how it is right now. You should ask Ha-Sung about Ramulator 2.0 when he gives a lecture about Ramulator 2.0. It was modular and extensible, although this became much better with Ramulator 2.0. So you should update this knowledge when he talks about Ramulator 2.0. And these are some of the other simulators that existed at the time. But one of the benefits of this sort of flexible simulation is you can compare many different standards. And that was actually the value that Ramulator added. You could easily, well, relatively easily model different standards. And these are some different standards. Run a bunch of workloads. In this case, we ran a bunch of workloads on a simple CPU model that we released with Ramulator. And this is what you could see, for example. This is actually the performance improvement of DDR4, for example, over DDR3. And you get some performance improvement, and this is the range across the 22 workloads. Not bad. And this is the performance loss of LPDDR3 or LPDDR4 compared to DDR3, as you can see. This is the performance improvement of HBM. So you can see some trends over here. This is the performance improvement of sub-array level parallelism, which is not bad, as you can see. So you can make design decisions like this. Even if you're not designing something new, you can use it to decide which type of memory I would use, right? If you know your workloads. Okay, so clearly this is open source. People have been using it. And we integrated with other simulators like Gen 5. These are sophisticated processor and system simulators, full system simulators, actually. I think we should work more on that integration and their reproducibility as well. And we had a project, Ramulator project course until last semester or so. So if you're interested, you can learn a lot more about this. So a much better Ramulator is Ramulator 2.0, and Ha-Sung will talk about that in the upcoming weeks. Do you have anything to add right now? Right now, no. Okay. But you can review these papers and you can also play with Ramulator. But I guess our lab is Ramulator, right? It's not Ramulator 2 yet. Oh, it's Ramulator 2 now? Okay, we updated it. That's good. So you'll work with a better Ramulator. That's good. Okay, we've seen a bunch of example studies using Ramulator that I'm not going to talk about. This is one study that we talked about in earlier lectures when we talked about latency, right? This is another study that's enabled by simulation. And basically, we can study a lot of different workloads, a lot of different DRAM types, and come up with different conclusions. For example, in this work, we actually saw that new DRAM types often increase excess latency so that you can get more bandwidth. And this is not good for performance on some workloads. Right? Some workloads actually lose performance with some of these, like DDR4, HMC, etc. And these were the key takeaways that we actually discussed in earlier lectures. So you can actually do a lot of interesting studies like this. And here, you cannot do any of these in a real system. As we have discussed in those lectures, in memory latency lectures, real system, you cannot have so many different memory interfaces. You need to buy completely different systems to have different interfaces. So you cannot buy a processor that has a DDR5 interface and also an HBM interface. Maybe in the future they will be, but today you cannot do that. But we want actually more on that, right? We want to study many, many things, right? So it's good to think about that. In fact, one of the comments, I don't remember if I made this, but one of the comments we received when we submitted this work the first time was, why don't you do this on a real system? No, maybe the reviewer should think a little bit more before making that comment, right? Yeah. Okay. So there are other studies that use Emulator, RowHammer. I talked about that at some point. Again, I'm not going to talk about that. A lot of these are open source. You can build on it. These are all free and open source. And having open source works enables really for other people to validate the results, build on it, provide feedback so that the simulator becomes better over time. Okay, and Osan talked about this, I think, in a research lecture in the past where he used Emulator. Was this 2.0? Okay, 2.0. I think everybody should use 2.0 going into the future. But then there are some things that Emulator does that Emulator 2.0 doesn't do yet. So is that true? Out of the box. For example, you don't have wide I/O modeling. That's true. I agree, yes. I agree, yes. So if someone wants to study wide I/O out of the box without modifying the simulator and understanding anything, which I wouldn't recommend to anyone, you may want to use Emulator. But there's no other good reason to use Emulator over Emulator 2.0 at this point, I think, unless you have backward compatibility problems. Meaning you've invested a lot into Emulator and switching to a new infrastructure will take time, right? That's also real. All of these are real, actually. Like people develop simulation infrastructures and there may be much better simulator, but they already invested a lot of their resources on some particular simulation infrastructure that's not necessarily the state of the art or good, but they have to continue because switching to a new simulator infrastructure is actually too costly in terms of time and the resources that they need to actually build on the new simulation infrastructure. This is the curse of software in general, right? You build a software stack and it takes a long time to change it to something completely different. Okay, there are many other ideas evaluated with the Emulator that we have seen. So there's Emulator for processing in memory, which is important, and you've seen some examples of this. I'm not going to talk about that, and you can find more information. There's some other useful simulators. Well, I guess we talked about Emulator too, but there's complicated simulators like Gen5 that do full system multi-core simulation. Rakesh is going to talk about MQSim. But there are also other simulators like MQSim that Geraldo has built for processing near memory. Next week or later, we'll talk about Virtuoso. And there are also fast processor simulators. And these simulators can be connected to each other. Not necessarily the interfaces are going to be good. So you need to do work on connecting different simulators also. Or you can always develop your simulator for your purpose. Right? It'd be good to know what you're doing, of course, when you do that. We actually did a lot of that when we started a lot of the memory controller research at Microsoft Research. The roots of Emulator actually go to a lot of the studies that we've done starting 2006 on memory controllers. Eventually, Emulator was taken over and made much, much better by my students at Carnegie Mellon, Yungu, and others to a point that it could be released. But the roots are actually much earlier, like 2006, and it got released in 2015, right? It's good to think about that. It takes a while to actually develop a simulator. Okay, this is the move. You can also find open source. And there's the PIM course that talks about that. Okay, MQSim, many more simulators online. Okay, I think I'm gonna, let me see how much time we have. Okay, not enough time. Are there any questions? Otherwise, we're gonna take a break. And after the break, the rest of the slides are on Virtuoso, which will be covered later on, and also some other types of simulators that you can study on your own, which are also very interesting, but completely different domains. People do simulation in other domains also. These are some of our works on agent-based simulation. And also we've done simulation of COVID-19, which is also interesting. So you can actually do simulation to study many, many things actually, than beyond computer architecture. Okay, so no questions. So let's take a break until 14:47. And after that, We'll start with Rakesh talking about MQSim, and then we'll go to PiDRAM with Ataberk. All right.
The slides moving on YouTube. What? Are the slides moving on YouTube? Are the slides moving on Zoom? I just wanted to ask. Onur, can we start? Okay. Let's start with the next presentation. So today I'll be discussing MQSim, which is a state-of-the-art SSD simulator. And we'll discuss some challenges that we need to look at when we model the internals of an SSD and how we achieve this with MQSim. So a brief introduction, I have been a PhD student here since 2021, and previously I was in the industry. My research interests include storage systems, flash memory, some machine learning and hybrid storage systems. And I'll be happy to talk to you about our projects and if you have some ideas. So I'll jump to MQSim, which is a framework for enabling realistic studies on modern multi-queue SSD devices. And this work was published in FAST 2018. So I'll jump to with an executive summary. So solid state drives are continuously evolving with the increasing demands on performance and storage capacities from data intensive applications. So at the time of publishing this work, NVMe protocols or multi-queue protocols were evolving, and these were the new protocols. We also have seen new SSDs enter into the markets with emerging storage technologies like 3D Xpoint or Intel Optane SSDs. So current simulators, this is true even now, that they have not been able to keep up with these changes, and they don't support many major features such as multi-queue protocols, and they don't model the steady state behavior of SSDs, and also don't capture the end-to-end latency. So we did a small study and we compared the difference in execution times between the real multi-queue SSDs and also the best performing simulator, and it has a 60 to 85% error rate. So we introduced MQSim, which is an open source SSD simulator, and it models all the major features of the conventional SSDs, which are SATA SSDs, and also the NVMe SSDs. And it also enables several new research directions, which I'm going to talk about. It's highly accurate. We validate the performance of this SSD on the performance of the simulator on 4 real SSDs, and we see that it only has a difference of 6 to 18% compared to the real SSD performance. So this is the GitHub link to access. I would encourage everyone to go through the code. So I guess you've all kind of gone through this previous lecture on NAND flash memory and SSDs, but I'll just give a brief introduction. So there are, so an SSD has a backend and a front end. The backend is typically the substrate which stores the data, or the data storage units. These are memory chips, which could include flash memory, or you can also put phase change memory or MRAM or any other substrate. And the front end is typically doing the management and the control of the accesses. So there is a host interface layer, which implements the protocol to communicate with the host system. And this is where you will see the SATA protocol or the NVMe protocol being implemented. Then there is a flash translation layer, which is managing the resources of the SSD, and also it processes these IO requests. There is a address translation happening from the logical address to the physical address, and there's also a cache involved here, which for faster accesses and to reduce the constraint on the resources. And there are multiple chip level queues that are being used here to enable parallelism. So flash translation layer does all this. Then there are flash channel controllers, which are basically taking these requests from the FTL and then converting them to a sequence of commands that the flash chips can understand. And it also manages the data that is being transferred from the host while writing, and also gets the data when reading for read operation. So FTL, the main objective of the FTL is to perform reads and writes well. So during flash writes, you all know about the constraint of performing the writes or updates out of place, which means that you always write the data to a new page, which is erased, and you mark the old page or the old data as invalid. So this means that you also need to update the logical to physical mapping all the time, and you make use of the cached mapping table to improve the performance of these lookups. And after we write a lot of data to the SSD, you also need to perform garbage collection, because we have updated many pages and they are all invalid now. So you need to reclaim those pages, and this is done by the garbage collection routine, which you typically does it in the off the critical path of IO handling. So as I mentioned, there is a write cache, which decreases the resource contention and also reduces the latency. So let's look at some challenges that we need to that arise when we model the multi-queue SSDs. So state-of-the-art simulators typically model the SATA-based SATA protocol, which is a serial protocol where all the requests that come from different applications. Let me show you a figure. Okay. So they basically all the request streams that are coming from different applications get into a single queue, which becomes the bottleneck there. But what we did was we also compare the performance of several simulators on 4 real SSDs. These are NVMe SSDs, and we see that the best performing simulator actually has an error rate of around 68 to 85%. So why is the error rate so high? This is because they don't implement some of these major features like multi-queue protocols, the steady state behavior, which we'll come to in a few slides. And also it doesn't model the end-to-end request latency. So they only model a part of the latency that happens within the SSDs. So so coming to SATA protocol, this is a protocol that has been inherited from the hard disk drives, and they only offer a throughput of around 1,000 IOPS or in the order of 1,000 IOPS. And it basically is a lot of responsibility lies on the operating system to perform the scheduling and also the fairness, to manage the fairness of IO requests. So here you see 3 processes which try to push requests to the SSD in their own queues, but there is an IO scheduler which schedules these requests into a single hardware dispatch queue. And this is from this hardware dispatch queue, the SSD consumes these requests and tries to service those requests. So there is also a native command queuing feature which tries to reorder the requests in this hardware dispatch queue and then try to improve the performance there. Now, if we look at a modern NVMe protocol, then what happens is it provides a lot of parallelism, and it also gives a significantly higher throughput in the order of millions of IOPS. And the reason is it basically provides parallelism in the by even enabling the per process queues in interfacing with the SSD. So what happens here is that we kind of bypass the OS intervention, and then the SSD must perform scheduling and ensure fairness. So the processes can directly submit to queues which are accessible by the SSD. So no existing SSD simulator, okay, at the time modeled this kind of a feature. And we also show in the paper how these multiple queues in the real MQSSDs affect performance and fairness. So the other challenge is how do we evaluate the steady state performance of the SSDs. So SNIA, which is the industry body, suggests that we need to assess the performance of an SSD only in its steady state. So what is steady state and what is fresh out of the box? So fresh out of the box is when the SSD is, there are no writes that have happened to the SSD, and the cache is not warmed up. So everything is fresh. And in these devices, there is no garbage collection does not happen. So as I said, write cache is also not warmed up. So many previous studies, so what we need to look at is when we perform a lot of writes to the SSDs, as you may have seen with your own devices, after a point when there is a lot of data, the garbage collection and other maintenance activity starts kicking in, and you kind of observe latencies or observe reduction in performance. So the challenge is many previous studies incorrectly simulate SSDs as fresh out of the box devices. And when we want to reach the steady state in most simulators, it takes a long time. So we see that prior simulator takes, if we have to perform preconditioning to reach the steady state, it takes around 80 times the execution time. And also another challenge is that many of the open source workloads that we have, they don't actually generate data which can fully exploit the capacity of the SSD, which means that you don't actually have enough data with these workloads to perform the steady state preconditioning. So existing simulators don't model these steady states and are very slow to reach the steady state. The third challenge is, as I mentioned, is to model the request latency completely. So you see that the request here, we show the read request. It goes through several hops here from the user application to the flash chip. And the major latency that we see is in terms of the flash read, because the other operations is just submitting commands or just submitting requests from one layer to another, and that takes very less time. But the flash read operation in a typical TLC SSD takes around 50 to 100 microseconds. And the other major contributor to the latency is the transfer from the flash chips to the SSD controller. So some of these current simulators only model the steps 5 and 6, which is in the back end here. Yeah, here. Okay, so what if we use a different non-volatile memory technology? So here we show the case of a 3D X-point SSD, where you have much lower latencies for flash reads and writes. So from 50 microseconds, it has come to less than 5 microseconds. And your data transfer also reduces because you transport smaller chunks of data from the flash chip to the SSD controller. But there can be, I will explain one case where other steps can consume a lot of or contribute to a lot of latency, and that other simulators don't model that. So here you see the request processing step number 3. So if this is basically, this step involves that you look at the cache for the mapping translations, the logical to physical address translation, and if you get the address translation immediately from the cache, you go and access the data. But if the address translation is not there in the cache, then you have to go and fetch it from the backend. So this process can take a long time if you actually end up going to the flash chips. So this can be a major contributor in that case. So other simulators don't actually model all these parts, so which cause inaccuracies for new NVMs. So in summary, these are the three challenges: the implementation of multi-queue protocols, steady state behavior, and end-to-end request latency. And our goal is to develop a new simulator that faithfully models features of both NVMe and SATA-based SSDs. So any questions so far? So let's jump to the design of MQSim. So MQSim models both SATA-based SSDs and NVMe-based SSDs, and it implements all the three challenges that, or addresses all the three challenges that we just described. And I'll just give you a brief description of all these things. So you have a host interface layer in the front end, which looks at the, there's a request fetch unit, which gets it from the process queues that are implemented in the host. There is an input stream manager. There is a data cache manager, which looks at the cache that is there in the DRAM within the SSD and then manages the data there. It could be reads, write data, or when you bring the data from the flash chips, you also place the data in the cache. Then you have the FTL, which looks at address mapping. It also manages the mapping table in the cache. This is only a part of the translations that are there in the cache. And then the flash block manager, which performs the allocation of or when you want to write, when there is a new request, you want to decide where to write. So this is partly handling the where leveling and so on. So there is a transaction scheduling unit, which is basically deciding which chip and which plane or which die the request goes to. And there is in the backend, you have the NVM channel and the NVM chip. So the strength of the simulator is that all of this is completely modularized. So you kind of, if you want to change something in one part of the simulator, it doesn't affect the other parts. And it also supports emerging non-volatile memory technologies. So this is completely open sourced, and it's an event-driven simulator, which means that you basically add everything that add all the operations that happen within the simulator as events, and you basically skip the time between the two events so that you can accelerate the simulation time. And it also is it's written in C++ and it's open sourced under MIT license. So now I'll come to so I would encourage people to go to the repository and look at this code. There are a lot of parameters that we provide in terms of whether if user can set that and basically play around with different configurations. So now I'll jump to the experimental methodologies. So how do we validate the simulator? How do we know that the simulator is better than all the prior simulators that we have? So we took 4 real data center SSDs with different flash technologies like MLC and TLC. And all of these use NVMe protocol because it was designed with NVMe protocol in mind, the simulator. And then we also precondition the SSDs to write 70% of the available logical space. And we also validate using multiple IO flows, which means that there are multiple applications sending requests to the SSD. And here, when we talk about flow, we mean the request stream from one application. And we set the queue depth in some of these experiments, which determines how intense these applications are or the request stream is. So that's one factor that we need to look at. And here we show some results, but there are a lot more results in the paper. So first we look at how accurately we can model the interflow interference. And here we see the three metrics. One is slowdown, throughput, and fairness. So this is on a real SSD, and I'll show you the results for MQSim next. So what we show here is a slowdown. How do we measure the slowdown? Is basically the response time that a flow gets, or a request in the flow gets, when it is run with other flows compared to when you run it alone. So that's one of the metrics. Then, so what we see is for when you, so here what we do is flow one is we have a static queue depth, which means that the intensity is kind of constant, but we vary the queue depth of the flow two, and we see that because of the interference, the slowdown of flow one actually increases, and the throughput reduces. In case of flow two, since the flow one is quite stable in terms of its intensity, it doesn't affect the performance of slowdown of flow two so much, and the throughput is also increasing because flow two is the major application here. And in terms of fairness, so fairness is basically, if I have to tell in simple words, it's how does the slowdown affect all these flows that are currently running. And we see that as you increase the queue depth, the fairness also reduces because flow two is able to get more of the resources and so on. Now, coming to how MQSim models this, we see that MQSim actually performs the, or we see the interference modeled very accurately. So you can basically see some correlation in terms of the results between a real SSD and MQSim. Now, I'll quickly jump to the next set of results. So we also observed that in one of the SSDs, there is a inherent control mechanism to provide some fairness, which means that so what the SSD does is basically it blocks the bandwidth available for one of the flows so that it cannot exploit all the resources available. So here we see that kind of a behavior where when flow two actually increases, the queue depth of the flow two is increasing, you still see that the slowdown has kind of stabilized, and your throughput also is kind of stable. And we see that with flow two, it is always stable, and then the fairness also remains stable at some point. So with MQSim, we are also seeing that kind of a behavior. We are able to model this controlling of interflow interference, and we see that MQSim can do that also. And this is basically done by allocating different channels for the different I/O accesses. So MQSim is able to model the control mechanisms. Now let's look at the steady state behavior with MQSim. So MQSim, it includes a efficient SSD preconditioning mechanism, which is very fast. Does not need to actually execute all the requests, because what it does is it sets the metadata so that when you we get the sense that it is already preconditioned to let's say 70% of the SSD. And you can also so it can be disabled to simulate fresh out of the box device as well. How do we do that? So we read the input trace, perform some statistical analysis, scan the entire storage space, change the status of the physical page based on the analysis. That's basically setting the metadata. Now, how do we? So what is how does this help in our getting accurate results? So you see the read response time, and the write response time. And here we show the actual SSD, the behavior of the actual SSD, MQSim with no preconditioning, and MQSim with preconditioning. So you see that the behavior of no preconditioning is slightly different from the actual SSD and MQSim with preconditioning. So till it reaches the steady state, your response times are slightly inaccurate, which is what these prior simulators are. Yeah, I mean, they are doing that. So this is the same with write response time also. I think I'm running short of time, but I'll kind of quickly wrap this up. So this is the advantage of performing steady state or preconditioning to reach the steady state. Now, so what we have seen so far is how do we model these interferences, and what is the impact of preconditioning. So now we look at how we accurately capture the read and write latencies, and here we look at two synthetic flows. So the another benefit of MQSim that I did not mention is that we also there are two ways of handling the IO requests, or two ways of working with a workload. One is you can have a trace-based workload, which is having a set of requests that you have captured from real systems, and then you give that trace to the system, to MQSim, to perform the execution. The other one is a synthetic workload that the simulator can generate by itself. So here we look at evaluation using two synthetic flows, and we show this on a real SST, where you basically see on the read response time on the y-axis, and also the IO request size. We sweep across 4 kilobytes to 1 MB, and we see that MQSim, which is shown in black, is more or less similar to the performs similar to the real SST in terms of the read response times and the write response times, and the error rate is kind of very low, as you can see here. So that's the accuracy of MQSim on how it captures the read and write latencies on 4 different SSTs. So on average, we see that the difference is for the read latency, it's around 2.9%, and write latency is around 5%. So when we did all these experiments with real enterprise traces, we see that the overall execution time difference between the real device and MQSim is from 6% to 18%. So that's a major improvement compared to the other simulators. So, but also the other thing is that we don't, have a increase in the execution time. The execution time is still the same because we use the discrete event simulation. So finally, we'll look at some research directions that are enabled by MQSim. MQSim accurately models these two protocols, the NVMe protocol and the SATA protocol, and all the internals of the SST. And this is not being done in other simulators, as far as I know. The fairness and performance effects are also modeled very, very well in MQSim. And in the paper, or I have 3 slides, but I'll quickly flash them. We model the 3 major sources of contention: the write cache, the cached mapping table, and backend memory resources. So we use IO flows designed to isolate impact of contention at a single source. So here we see the interference at write cache, and we use 2 flows, where flow 1 has very high cache locality, and flow 2 has very poor cache locality. So which means that flow 2 can cause a lot of cache thrashing, because it generates a lot of random requests, and that can cause cache thrashing. So here we see the same flow down figure, where if you increase the intensity of flow 2, the slowdown increases for flow 1. So that's accurately being modeled for this kind of a so we model that for the interference at write cache. So similarly, we also look at the interference at the cached mapping table. So this is only for the mapping entries in the cache and the DRAM cache. And we again look at a flow where flow 1 is sequential, and flow 2 is split between sequential and random. And once we increase the randomness of the flow 2, we see that flow 1 observes a much higher slowdown than what flow 2 observes. So this shows that a more random flow 2 causes CMT cache thrashing and significantly lowers the hit rate of flow 1. Similarly, we look at the interference at the back end, which is, so the back end here means that the chip level queues that we have in the SSD controller or in the DRAM. So we see that two flows here concurrently performs random accesses, and one flow has low intensity and the other one has higher intensity, and we see the same behavior. So if one of the flows has very high intensity workload, then it means that the chip level queues are flooded with flow 2, and the flow 1 requests have to wait much longer. So this is another behavior that we model in MQSim. So in the paper, we also show some application level studies in terms of IPC, slowdown, and fairness. Now, MQSim has been used by our group and also widely used in the community for many of the research that is going on. This is a list of works that we have used that uses MQSim for performance modeling and also system level modeling basically. So we have a bunch of works, and these are works that are not from our group but also from the wider community which uses MQSim for evaluation. So conclusion, MQSim is an open source simulator which models all major features of NVMe and SATA SSDs, and it's very highly accurate, and we validate against 4 real MQ SSDs, and the error rate is considerably lower than the previous simulators. And I encourage everyone to go through the GitHub link, and you can play around with some traces that are available. And yeah, I'll be happy to take any questions now. Yeah. Yes. Mhm. Okay. Okay, yeah, I kind of noticed only one part. So here again, I mean, with interference, so it's basically we are looking at a real SSD and we are only able to take some pointers from how it works because we don't know all the internal details of that. So that's why there's still a kind of a gap between the slowdown of the real SSD and MQSim. What is the reason for this? It can be because I mean we are not modeling the FTL policies that are being implemented in the real SSDs in the same way. That's one possible scenario. Yeah, that can be one case. Yeah. Yeah, same trend. Yeah. Any question? Yeah, please. Preconditioning is not related to aging, but it can also affect the aging because preconditioning, what it does is it writes the SSD physical space to 70% of the capacity or 80% of the capacity, so that we get into a situation where the garbage collection and other maintenance activities are also happening at the same time as the IO request handling. So this is, as I said, fresh out of the box doesn't perform garbage collection. So you may not necessarily see the response times that you see when you have a garbage collection running. It's not the aging. So you basically write the entire address space of the SSD. You're talking about retries that you perform during error. Mm-hmm. Mm. No, I mean, if you're talking about retries that you perform during error correction, or I don't know if you're talking about any other scenario, this can happen. I mean, it can. There are some parts of the SSD's functionality that it cannot model because we cannot model error handling or those kind of scenarios. So that may not happen with MQSim, but we can, of course, model how when there are two processes running, you can also see the interference, right? So those kind of behaviors we can model. Yeah. Any other questions? Yes. Okay. There are no more questions, then thank you so much, and I'll pass it on to Athabak.
Okay. I'll get started when I fix this. Okay. I'll be talking about PiDRAM starting now. PiDRAM is an FPGA-based framework for end-to-end evaluation of processing in DRAM techniques. So we're looking at processing using DRAM specifically in this work. I'll start with an executive summary. This slide set is meant to be dense, like information dense. It's a conference presentation, but you can stop me to ask questions if you want to. Again, okay, going back. So commodity DRAM-based processing using memory techniques or processing in memory techniques can improve performance and energy efficiency of our systems at no additional, at least DRAM hardware cost. That's why they're interesting to study. But there are challenges of integrating these techniques into real systems that are not yet solved. And we think that general purpose computing systems or specialized testing systems and even system simulators cannot be efficiently used to study these challenges. And our goal is to enable a framework or develop a framework that allows us to efficiently study these challenges, basically. And our key idea is to develop an FPGA-based framework that enables these studies, system integration studies, and end-to-end evaluations of processing in memory techniques using real unmodified DRAM chips. We evaluate this infrastructure using 2 case studies on a real FPGA-based prototype. In the first case study, we study bulk data copy operations inside DRAM chips. We see that you can gain up to 119x in this case, in our case, speed up for copy operations compared to baseline CPU copy operations, even when you factor in system software support. And this will become more clear as I make progress in the slides. And you can get this done. You can make this study by only adding a relatively small number of Verilog code, lines of Verilog code, and some again, relatively small number of C++ code over PiDRAM's flexible code base. In the second case study, we look at in-DRAM true random number generation, and we see that this prototype can provide you with 8.3 megabits per second to random number generation throughput, where you need to spend like 220 nanoseconds to get the first number out. That's the latency. And this takes even fewer lines of code to implement over the existing infrastructure. All right, PiDRAM is also available at this link on the bottom, but I have a different slide that shows you the whole GitHub repository. So don't worry if you lost that link. This is the outline for the rest of the presentation. I'll start with some background on DRAM. You have probably seen this slide multiple times, but a processor's memory controller communicates with DRAM chips on a DRAM module through what we call a DDR interface. And each DRAM chip has multiple banks. Inside each bank, you have many subarrays. Inside subarrays, you have word line drivers that control, well, we will see what they do next. So operational details, I'll save them for the next slide. But you have word line drivers and sense amplifiers in a subarray, and multiple mats in a subarray that are separated by word line drivers. If you look at inside a mat, you see the 2D array structure of DRAM cells, where we call a row of DRAM cells really a DRAM row. And inside a cell, well, this is what a cell looks like. It's made up of an access transistor and a capacitor to store data. So we will look at how DRAM operates at the scope of a single subarray. And we basically, in this figure, we collect multiple cells under, well, a cache line, typically 512 bits, because the access granularity of DRAM is a cache line. On the bottom, we have a timeline of DRAM commands. To access a single cell or a cache line, you need to activate a DRAM row, which will raise a word line signal and connect all the cells in that row to the bit lines, and then the sense amplifiers will essentially store a copy of this row. And from then on, you can send read commands to read data from the row, or you can send write commands to update the values in the row. And then you pre-charge, and then you can activate another row. These are basics I hope you already know about for DRAM. So I'm going to skip the rest of the slide. Maybe not. So we have some key timing parameters that define the amount of time you need to wait between two subsequent commands that you send to your DRAM chip. The most important ones being the activation latency, but that's also called TRAS. That's the amount of time you need to wait between an activate command and the subsequent pre-charge command. The pre-charge latency, which is also called TRP, is the latency between a pre-charge command and the activate command. And we also have what we call access latency, which is the amount of time you need to wait, the duration you need to wait between the activate command and the next read command. If you violate these parameters, you can see interesting things happening inside your DRAM chips, which we will touch on in the upcoming slides. Now I'll briefly introduce commodity DRAM-based processing in-memory techniques. You already know about some of these also. They use operational principles of memory to perform bulk data movement or computation inside chips. And we knew back then, this is from, I guess, 2022, that commodity DRAM chips could already perform bulk data copy at DRAM row granularity, true random number generation. You can implement physical unclonable functions, and you could perform the majority operation in real DRAM chips. In our work, we're most interested in these first two. So I'll remind you the key ideas of them. The first one being row copy. Here, if you remember, the key idea is row clone. Basically, you have this source row that you want to copy and overwrite the destination row with. You need to, well, how can you do this? Given DRAM array operation principles, you activate the source row that copies the data to the sense amplifiers, and now you just need to copy it back to the destination row and overwrite the data there. The first operation already exists. It's an activate command inside DRAM chips. And you can do this in real DRAM chips, basically. But the second one, we'll see how we can do that in real DRAM chips. The idea is to use carefully crafted DRAM command sequences with reduced timing parameters. And we build on what Compute DRAM showed for DDR3 chips, They show that you could copy from one row to another row using basically reduced timing parameters. And this diagram is trying to depict in more detail what I mean by reduced timing parameters. If you don't reduce your timing parameters, if you obey the standard, this command sequence will result in the activation of row S, and then a correct pre-charge operation in the DRAM bank so that no row is open. And then when you send the activate command to row D, you will have row D activated in the end. If you violate the timing parameters and reduce the duration that you wait between the first activate command and the pre-charge commands, this will result in you activating row S, and then without pre-charging the bank, you activate row D again. So this is the operation that we wanted to do in the previous slide. We rely on reduced timing parameters to perform bulk data copy operations in DRAM chips and PiDRAM as well. Now for DRange, this is the in DRAM to random number generator, also called DRange. We leverage access latency failures. So this diagram shows you many DRAM cells, and they're sized and colored according to the failure probability when we access them with a reduced access latency parameter. So this means the smaller and the red colored cells have a very high chance to fail when we access them with the reduced access latency parameter. The green ones have a very small chance to fail. And interestingly, the yellow ones have a 50% chance to fail. This is completely random. And the key idea is to find these cells and continuously sample them so you can generate a random bit stream. And real DRAM chips can already perform DRange because you can reduce the timing parameter and just access your DRAM cell, access your DRAM chip. So we have seen a bunch of nice applications or real, nice processing using memory techniques that are supported already by real DRAM chips. But how do we kind of bridge the gap between, application, like you see the system stack here. You have an application that wants to do bulk data initialization, for example, and you want to back this operation up with the bulk data copy support inside the real DRAM chip. How do you bridge this gap? You need some support for custom timing parameters at the relatively low levels at the microarchitecture and logic level, so that you can reduce timing parameters programmatically, right? You need some sort of control for processing in-memory operations in your memory controller, for example, that orchestrates the execution of a row clone operation. Some support, some software interface to allow the programmer to make use of the capability, the processing and memory capability, and a supervisor software that provides basic system support, such as data placement that can enable a row clone would be very nice, because then you don't have to implement your own data placement routines, and you don't have to worry about them, basically. So PiDRAM's key idea is to basically bridge this gap with customizable hardware and software components. That was a very slow entrance to PiDRAM, I guess, but hopefully everything is clear so far. And in doing so, we want to allow users to rapidly implement processing and memory techniques and solve system integration challenges, and also analyze end-to-end implementations of these real processing using memory techniques. So our goal is to provide a flexible framework that's useful for studies on commodity DRAM-based PIM techniques, as I said, and to basically guide our design. We look at the system requirements shared by different processing in-memory techniques, and we come up with four components that will enable this: 2 at the hardware level, 2 at the software level. The first one is the PIM operations controller that basically executes PIM operations. Again, this is very high-level descriptions of these, but we will get into details. A custom memory controller that you make use of to perform these reduced timing operations. And at the software side, we have a library that provides an interface for application developers to make use of these operations, and then a custom supervisor software that provides the basic system support. We attach these key components to a real RISC-V based computing system to develop PiDRAM's system design. In the system, we implement the PIM operations controller and the memory controller as like hardware modules, as I said. And we have the extensible library, PIMLib, and the supervisor software as software components in the system. So I'll describe each of these using the diagram. But we also have the basically RISC-V core and the DRAM module that we work with in this system. We'll start with the first one, that being the PIM operations controller. It basically decodes and executes PiDRAM instructions to perform processing and memory operations inside the DRAM chip. It's connected to the hardware system as a memory mapped module, meaning that it receives PiDRAM instructions over the memory interface, over the memory bus from the RISC-V core. And there are 3 registers here depicted as instruction, flag, and data that are accessible over the memory bus. And this makes it easy to port PIM operations controller to another system that would use a different ISA, basically. And it communicates with the memory controller using a simple interface whereby it sends a request and then waits for it to complete and then read the results of the operation from the memory controller. And when we look at the memory controller, it performs these operations by reducing the timing parameters and sending custom DRAM commands to the DRAM module. It supports conventional operations like load and store, and it implements what I would describe as an easily replicable state machine per operation, so that you can just copy it and paste it, and then modify it slightly to implement a new one. Hopefully that makes it extensible. And the physical interface component here, it controls the physical signals in the DDR3 interface. It receives DRAM commands from the scheduler, and then it just operates the DDR3 interface, basically. On the software side, you have the PIMLib, or PIM operations library, that encapsulates customizable functions that interface with the PIM operations controller to perform those operations. And we expose this functionality to software using PIMLib. And for example, to perform a PIM operation, a typical function in this library will use a bunch of load and store requests to access the memory map registers in the PIM operations controller. So later, I will describe the protocol that they obey while basically perform these operations. And the last component, which is the custom supervisor software, it exposes PIM operations to the user space, and we also implement some necessary, or what we consider necessary OS primitives to basically allow the users to develop applications more easily. So these are, for example, memory management and allocation for in-DRAM copy or row clone operations. So we'll look at a full picture, like I'll describe the execution flow for a processing in-memory operation in this framework. As an example, we will look at what happens when the user calls the copy function to perform an in-DRAM copy operation. The user will make a system call to this copy function to copy n bytes from A to B. These are 2 arrays. The custom supervisor software will find the physical addresses corresponding to A and B, and then calls the copy function in the PIMLib with the semantics that are shown here. And it takes 2 arguments, basically, S and D. S is the address of the source DRAM row, and D is the address of the destination DRAM row. Oh yeah, this is another thing that shows the same semantics. The copy function will execute 2 store instructions in the CPU. The first one will store the instruction. Basically, it will store the instruction that will perform this operation in the instruction register. And the second store instruction sets the start flag in the flag register to initiate the PIM operation, basically. And when the start flag is set, the operations controller instructs the memory controller to perform this operation in the DRAM copy operation with from row S to row D in our case. And when the memory controller acknowledges this request, it will set the acknowledged flag. This 7 here that you see. Yes.
So how does the IEDM memory controller
So here, basically, when you run this library function, what will happen is you store it. So when you set the start flag, that's also a store instruction being executed, right? That will then the PIM operations controller will explicitly instruct the memory controller to perform the operation. So there's no polling going on basically. So like the interface is not polling based. Okay. So yeah, you have the acknowledge flag set that indicates to POC, PIM operations controller, that a new operation can be started basically. And when it's when the acknowledge flag is set, the memory controller starts working on generating the command schedule that it needs to execute to perform the PIM operation, and does that. When it's done, it says the finished flag, and then, well, not then. Meanwhile, the PIMalib software. Maybe you were asking about this actually. The software will continuously poll actually one of these control registers. Either acknowledge or finished based on what the programmer wants to do. And then once the operation is done, your blocking call at the software level returns. So you can continue running your program. We didn't use the data register in this example because the result of roll call operations is still inside the DRAM chip. You don't have to copy any data to some intermediate register, but we will make use of that in case when we want to generate random numbers and buffer them somewhere. That's what this says. So in short, we implement 4 key components, 1, 2, 3, 4, to orchestrate processing in memory operations in PiDRAM. We develop a prototype of PiDRAM's full system on this board, Xilinx DC706 board. It comprises a 5 system that's made up of a rather wimpy core and with some L1 data and instruction cache, as well as a TLB. Its clock frequency is 50 megahertz. And we enable PIM operations in the DRAM modules that you see here. And it's also under this cage. There's a DRAM module, I promise. We use that one to perform real processing using memory operations. So I'll continue with the case studies that we did. For you to recall, we need to reduce timing parameters to perform roll call operations in real DRAM chips. And to do that, we extend PiDRAM memory controller with a new state machine that controls this sequence with reduced timing parameters. And we then expose this operation to PIMalib by implementing in the copy instruction in the PIM operations controller. And these 2 modifications take only 198 lines of Verilog code. Okay, you have a question? Yes. So the component that handles the alignment, I will come to that actually in 2 slides from now on, but very quickly, like the system software handles that alignment when it's doing the mapping for, when you want to allocate the 2 operands, you will explicitly instruct that you want them to be able to copy to each other. And then you place it that way. Yes, at least the support we provide in PiDRAM assumes that. But maybe you can find something new that's more flexible using PiDRAM. Or you don't have to use PiDRAM for that, but cool. Then once we have support for roll clone implemented in the infrastructure, we studied 2 challenges that we could identify in implementing roll clone end-to-end in a real system. The first one is proper memory allocation for roll clone operations. We will discuss this in detail. The second one is maintaining memory coherency. Now, because you're moving data inside the DRAM chip, and data in the DRAM chip can also exist as copies in your cache hierarchy. You want the most up-to-date data in DRAM when you're doing this operation. To solve the second challenge, which is relatively easier to describe. We implement cache line flush instructions in the RISC-V CPU. We use them to evict the cache blocks that correspond to the source and destination operands before we perform the row copy operation. And for the first one, let's go into a bit more detail. So we identify 3 memory allocation requirements to be able to correctly perform row clone operations. This diagram describes you 3 problematic allocations and 1 good allocation, I would say. And you have 2 different banks here, 2 different subarrays in each bank, showing you the different cases. The first requirement we identify is what we call the granularity requirement. It requires that operands must occupy their DRAM rows completely. Because if they don't, then you're overwriting the data that's mapped to here, maybe that's used for something, with data that's garbage that's in the source operands row. You don't want that. The second requirement is that they need to be, I will use the word aligned, but basically the start offsets for both operands must reside on the same bit line, because you can copy only data from basically from one cell to another cell if they reside on the same bit line. That's the alignment requirement. And the third one, what we call, is relatively simpler to understand, was mapping, because you can only copy bulk data at row granularity within a subarray. You're bound to operands that exist within the same subarray. You cannot put them in different banks or in different subarrays. You have to put them in the same subarray. And the fourth mapping satisfies all 3 requirements to basically to allow the users to allocate their data that satisfies these requirements. We implement a new memory allocation function. And its goal is to allocate virtual memory pages that are mapped to the same DRAM subarray, aligned with each other. It has these semantics. I won't go into the details of how this is implemented, but at the core of it, there's what we call a subarray mapping table. This is a structure maintained by software and the supervisor software. You have, let's say, instead of a malloc call, you have alloc align calls. In case you want to allocate a 4 kilobyte large array, you want to indicate a subarray ID for this. So if you allocate 2 separate arrays with the same subarray ID, this function ensures that they go into the same subarray. Therefore, you can copy from one operand, well, I will use the word object or array to the other array. How it works is basically you get a physical address that points to a DRAM row in subarray 0 by asking the subarray mapping table, and then you update the page table with that, with what you get from the subarray mapping table. How this is implemented is much more complicated than what I'll go into, but we have a basic detailed description of it in the paper you can find it at this link. So I'll move on to evaluation. Describe you our methodology. You already are aware of parts of the methodology. We have a small core, 50 megahertz core. This table shows you the system configuration. We run 2 micro benchmarks called CPU copy and row clone copy. These are quite intuitive. CPU copy is just using load and store instructions to copy arrays. Row clone copy uses in-DRAM copy operations to do the same thing. We evaluate row clone copy operations with and without CL flush, meaning that we evaluate 2 cases where in one, all the data is up to date and resides in DRAM. In the second case, well, we evaluate actually multiple configurations of where the data, which parts of the data is where, but we're trying to understand the overheads of maintaining coherency using CL flush. We have copy and initialization heavy workloads. Those are fork, bench, and compile. And we also were able to run a workload from spec 2006, is libquantum, where we replace calloc calls. These are used to initialize, let's say, an array with all zeros or any value that you want to initialize it with. And we replace them with in-DRAM initialization, bulk initialization, and instructions, basically. This 8 kilobyte row size determines the granularity of in-DRAM copy and initialization operations. So if you want to do an in-DRAM copy, it must be at least 8 kilobyte size. Okay, so this plot shows you the throughput improvement provided by in-DRAM copy and initialization operations over CPU copy and initialization operations for different array sizes that you see here. Here we assume that all data is up to date in DRAM, so there's no CL flush. And we have different arrays, as I said, different array sizes on the x-axis. We observe that you can improve copy and initialization throughput by 119 times and 89 times using in DRAM copy and initialization operations. When you look at CL flushes overhead, things go a bit sideways. So here you see the same throughput improvement. And on the x-axis, we have dirty cache block proportion. If you, for example, have 0% dirty cache blocks, this means that all, so these are 8 megabyte large arrays, by the way, all of the data is cached, but all the copies are clean. So you don't have to write anything back to DRAM. You just have to invalidate the destination pages or cache blocks. And the opposite case, in the other extreme, 100% dirty, you have everything cached and everything needs to be written back. And we observe that CL flush operations dramatically reduce the potential benefit you can get with in-DRAM copy and initialization operations. I'll summarize the results for other workloads in this slide. We look at fork bench. This is basically simulating the fork calls you make when you want to copy a process, right, and start executing it immediately. The x-axis shows you how many pages are copied when you make a fork call. So towards the right, you have an increasing number of data that must be copied. On the secondary y-axis here, you see the fraction of time that your workload spends on memcopy. And on the primary y-axis, you have the speed up that you get by doing those copy operations using in-DRAM row copy operations. I guess to summarize, we see that performance improvement increases as the fraction of data that you must copy increases as well. For compile, we see a 9% execution time reduction provided by in-DRAM initialization operations. This makes sense because only 17% of compile's execution time is spent on initialization. And finally, for libquantum, we achieve 1.3% end-to-end execution time reduction. And we estimate only 2.3% of libquantum's time is spent on initialization. So this result kind of makes sense if you consider these two numbers or these fractions. So I guess this infrastructure is kind of unique in the sense that it allows you to run a real workload from beginning to end, which is libquantum. You wouldn't be able to do this with simulation if you didn't have months to spend. But this, I think, for us, this took like a day or two to do. Yeah, that's the remark I will make about this slide. And I'll move on to DRange, the true random number generation case study. Just to remind you, the idea we're trying to find cells that fail with 50% probability when we access them with reduced timing parameters. So we do that, we find those cells, and we continuously sample them to produce a large random bit stream. We periodically generate these in PiDRAM and store them. So basically, the way you generate them is you have to reduce the access latency and access that cell you profile to be random. We put them in a 1 kilobyte large random number buffer in PIM operations controller, and then the programmers can read these numbers by using a new function call we implemented in PIMalib and also the supervisor software. And they took this many lines of code to implement. We also evaluate we develop a micro benchmark to evaluate the throughput of our true random number generation support. And here you see on the x-axis the programmable period at which the PIM operations controller performs this random number generation process. And on the y-axis, you see the TRNG throughput that you have. Basically, you can achieve up to 8.3 megabits per second throughput if you are willing to perform this procedure every 220 nanoseconds in the memory controller. This would contend with other memory requests, basically, but we have not evaluated that in this case study. Basically, the trade-off is as you go right, the less memory contention you expect. As you go left, the more memory contention you would expect. So I think I'm done with PiDRAM. Maybe the throughput is low because the throughput is not low. If you look at only this slide and you have no idea what a true random number generator can achieve in DRAM, you can expect up to gigabytes per second, gigabits per second throughput from a single DRAM channel. There are many reasons, but the most important one being we cannot exploit or leverage bank level parallelism with this implementation. But perhaps with some small tweaks, you could actually make it exploit bank level parallelism and generate more random numbers, basically. That's one reason. No, but there's no fundamental reason why you cannot. It just would take more time to develop the case study. Much more than simulation, basically. If you're simulating this, maybe the code you want to change is 10 lines in some C file. Here, it's a bit more difficult to achieve. Do you have any questions? Yes. Yeah, that's a good question. So the question is, how do you deal with in DRAM remapping when you're doing this allocation for row clone? I think, so this is not clear because I didn't describe how we create the subarray mapping table or fill it up. But you have to profile your DRAM chip. So you basically test a bunch of source destination address combinations and you figure out which ones succeed. And once you have that information, you kind of bypassed or you worked around the in-DRAM mapping implication. Yes, you need to do that, but hopefully once per DRAM module in your system. I don't have a number at the, off the top of my head, but it's not prohibitive. Yeah, we do it all the time. Yeah. You do it offline once, hopefully, and that sticks for a long time. We have not observed the mappings changing over time, so maybe they will. Don't know. Okay. So how much time? Okay, I have like 30 seconds. PiDRAM. I will skip the executive summary. I'll show you the GitHub repo. We have it on we have everything open sourced, including everything I've told you about. Basically, is open sourced, and we have a extended version of the conference. Well, not conference, journal paper in archive at this link. And I have a longer talk / tutorial on YouTube from 2021 on PiDRAM. And if you're interested on PiDRAM, maybe this is a good idea. It's a good idea to watch this because I talk about the mapping or the allocation methodology or mechanism in more detail as well. That's all for PiDRAM. I was planning to talk about DRAM Bender as well, but I guess, are we out of time? What do we do? Okay. Are there more questions? Yes. You need a much detailed memory controller. Detailed is not the right word, but you need to put much more effort in modeling a detailed memory controller. I'll use the same word again. I couldn't avoid it. Yes. Yeah, that's a good question. So the alternative to implementing PiDRAM's memory controller is to maybe use a memory controller provided by the FPGA vendor, basically. We don't have results that compare the performance of that memory controller to what we have developed in the paper, but I remember doing this like offline, trying to tune the memory controller that we have so that it extracts as much performance, at least as much performance as what employing the alternative would give you. So I will say there's no, I don't expect a degradation in performance, but you can always improve the model much more to make it more performant. Any other questions? If not, then I guess we conclude this lecture. So thank you everyone for listening. And that will be all.